Okay, everybody, so in the last lecture we were going through how to do the pH of a buffered solution, but now let's try to calculate pHs for both buffered and unbuffered solutions, and even consider what would happen if we added some acid or base to a buffered solution. So the problem is with the acetate buffered system. We were just looking at acetate a minute ago. They're not kidding. These are important for biochemical studies. I've made my own acetate buffered solutions to work with different enzymes if you want them to be in a lower pH range than what you would typically expect for, say, the bloodstream that we looked at that was up around 7.4. So this is going to ask us to do a calculation like we did in the last video, which was to come up with the pH of this solution after you add together some of the weak acid and some of the conjugate base. So then the second part of this is going to be, now that you have that solution, what happens if you add some additional sodium hydroxide? So we're going to add some OHs to that system. We'll do that in a different volume, so there'll also be a volume calculation. And then finally, a third part is going to be, what would happen if we had started off with an unbuffered solution, which was just pH 7.4, and then added some NaOH to it? What would happen to the pH? So here we are in part 1. The part 1 is to calculate the pH. Now we can do this with an ice table, and I've done it that way in some of the previous examples. I've done it this way for this problem, and I come up with the exact same answer as if we use the Henderson-Hasselbalch equation. So let's go ahead and do that. So here's the equation. Because this is a shortcut, this would be a much faster way to do it. The information that's already available in the problem to us is going to be the concentration of the starting acid. This acetic acid is the HA. That 0.10 is going to come down here in the bottom. The 0.10 molar acetate, right, that's what's going to dissociate and become that anion. And so that number is going to come up here in the top. So now what we're going to need is the Ka, and we've already worked several problems now with acetic acid. You could look that up or remember that it's 1.8 times 10 to the minus 5. That's the Ka that we've been working with. And so now let me plug in all those values, and then I can go ahead and start to simplify. The negative log of 1.8 times 10 to the minus 5. And then an interesting thing happens here in the next part. 0.10 divided by 0.10 is 1, and the log of 1 is 0. So this is going to be a pH that is equal to 4.74. So that was a lot quicker than using an ice table, and we went ahead and got immediately to that pH. And we can use this information in the next part of the problem. So in the next part of the problem, they're actually taking this nice buffer system that we just made with a specific pH, and they went ahead and added in some sodium hydroxide. So they're adding some OHs, and so we think about this conceptually as a buffer is able to resist a limited amount of OH or a limited amount of protons that are added to the solution, so that it's not going to change the pH very much. So we may end up getting an answer where the pH didn't change very much. So I think also it's helpful to think about this in very conceptual terms. So let's draw out what we're actually doing. So right now we have a buffer solution. So I've just drawn, a beaker with some of this buffer solution in it. And in that solution, we have a mixture of the weak acid, acetic acid, CH3COOH, and then we also have some of its conjugate base. We have some amount of CH3COO-, and for every one of those, we've got an Na plus floating around. Okay, so we've got this, and they're saying that we have 100 milliliters of this buffer solution. And then what they want us to do is they want us to come in with another 1 mil of our strong base sodium hydroxide. So the idea here is that when you mix these two together, we're going to have a volume change. We're going to end up with a total volume of 101 milliliters. And then what we're going to have is these OHs trying to cancel out the H's on this acid. So in an acid-base neutralization, we take the base and the acid, we put them together, and they see how many of each other they cancel out. One of them will be a limiting reagent. You'll have a limiting amount of OH or of acid, and then you'll adjust the pH based on whatever's left over. So that's what we're going to do in this problem. So in this problem, let's actually think about it in two parts. Let's first think about it as a neutralization reaction and then worry about calculating the pH. So the neutralization reaction can be written like this. And we have the acetic acid CH3COOH coming together with that strong base NaOH, and they're going to react to form a salt and water. That's what we get every time we have a neutralization. That salt is going to be sodium plus and acetate CH3COO minus, and of course the water. So now we have the nice balanced equation written for neutralization. Now, neutralization is going to occur with a certain number of molecules of NaOH interacting with a certain number of molecules of the acetic acid. And so we need to think about this in terms of moles, not the original concentrations that they gave us. So we need to calculate the number of moles of everything we're talking about in this balanced chemical equation. So we have initial concentrations for every one of the compounds that are involved in this chemical reaction, and now we can also consider what that means in terms of moles per liter. So you may recall that that molar concentration means that many number of moles in 1 liter. So if we have 0.10 molar CH3COOH, we actually have 0.10 moles of that acetic acid in 1 liter. But we don't have a full liter of this, which means we don't have a full 0.10 moles of this compound. We actually had 100 mils of this, so we need to multiply this number, 0.10 moles per 1 liter, by the number of liters we actually have. So we're going to multiply this by 0.100 because that is 100 milliliters, and that will give us a number of moles. And so we do that calculation and we see that it's 0.01 moles of that acetic acid that we actually have in solution that could interact with that sodium hydroxide. So we're going to do the same type of calculation for the other two compounds that we have. We'll do the sodium acetate and the sodium hydroxide to get the number of moles. So it ends up being the exact same number for the sodium acetate, but a smaller number for the sodium hydroxide because we only have 1 milliliter or 0.001 liters of that sodium hydroxide. So we actually end up with 0.0001 moles of sodium hydroxide. So now that we have starting concentrations of these compounds, we can go ahead and put this into an ice table for the reaction and figure out what's left over. I rewrite my balanced chemical equation. I've got my initial, my change, my equilibrium. Water's not going to contribute to this. How much of the acetic acid do I start off with? I have 0.01 moles. How much sodium hydroxide do I start off with? 0.0001 moles. How much of the sodium acetate do I start off with? 0.01 moles. So you will notice in this ice table, I'm not using the concentrations, I'm using the moles. But if you take a step back and you think about it, with us using concentrations, and in all the reactions we've talked about previously, if you hold the volume constant, then you could actually be talking about moles, right? You could just convert those over into moles instead of those concentrations. So it's perfectly fine to put moles in this table. We just want to make sure that we're labeling the units here so we know we are in fact talking about moles and not, say, a molar concentration. So great, we have those initials, and then what's going to happen? So in this reaction, we only added a little bit of that sodium hydroxide. We figured out how many moles that is. That's a small number of moles of sodium hydroxide. So in this reaction, sodium hydroxide is going to be the limiting reagent. That means we are going to use it up completely. So we're going to subtract 0.0001 moles of sodium hydroxide because we're going to use it completely. If we're on the same side of our arrow of our balanced chemical equation, we're going to use that same negative sign to say I'm going to take away 0.0001 moles of that acid, because that's what I'm neutralizing. And then on the right side of our ice table, we switch the sign of our operation. So that means that if we are consuming some of the acetic acid, we're actually going to be making some of the sodium acetate. So we're going to add 0.0001 moles. And then, of course, in our equilibrium, we're going to just go ahead and balance that. So now we've got 0 of the sodium hydroxide. We used up all of our limiting reagent. We're going to end up with 0.01 0.01 of our sodium acetate, and we are going to end up with a smaller number of moles of that acid because we actually canceled or neutralized some of it. So we've got all these moles here, and now we have used our ice table to figure out how many moles of the acid would be left over and how many moles of the conjugate base would be left over. So now we have the type of information that could go into the Henderson-Hasselbalch equation if they were only concentrations instead of moles. So let's turn them back into concentrations by considering that we had a total of 101 milliliters. So I'm just going to take the moles of each one of those compounds and divide it by the volume, that 101 milliliters. Now 101 milliliters is the same thing as 0.101 liters, so I've gone ahead and made that conversion before I do the division, and then I just solve. And I get 2 molar concentrations, the types of things that I need for that Henderson-Hasselbalch equation. So because of space reasons, I'm going to go back to the top of this page and write the Henderson-Hasselbalch equation and then start to fill in this information. And so I've started to fill in my information. It's going to be the negative log of the Ka of acetic acid, or negative log of 1.8 times 10 to the minus 5. And I'm going to add that to the log of the ratio of that anion, which is going to be the acetate ion, 0.10 that I have down here, and then divide that by the starting acid concentration. So that's going to be the 0.98 concentration down here. So I plug those two things in. So simplifying this, I'm getting an answer that looks like 4.7487. Now I'm going to want to round this. I'm probably not keeping track of my sig figs correctly, but I don't need to if I want to show you how little of a change, right? So if we round this to 3 significant figures, you see that we have a pH of 4.75. Now, if you recall back from the first part of the problem, part A of this problem, we had a pH of 4.74. So this buffer system resisted a very big change in the pH, and we only went from 4.74 up to 4.75 when we added 1 milliliter of that very strong base. And so that is the purpose of a buffer, to resist the change in pH, and we didn't see a very big change at all. So the next part of this problem is going to say, okay, let's just do a comparison where we didn't have a buffered system, and let's just start off with something that has a pH of 4.74, and then just add in that 1 milliliter of the sodium hydroxide. So it may be helpful to think about this conceptually as well. We have some unbuffered solution. It's based in water. Now it's acidic in pH, so we've got H3O pluses in there. We've got more H3O pluses than we have OH minuses. So we'll say there's 2 of the H3O pluses and only 1 of the OH minuses. So that should give us a pH down here that is acidic, something like 4.74. So that's what we have, and that's what we're starting out with, and we have 100 mils of it. And so then they're asking us, can we just take and put in 1 extra milliliter of that sodium hydroxide? So when we add that in, that sodium hydroxide is going to interact with the acid on a molecule by molecule level, or on a mole by mole level, in order to cancel it out. So we need to actually have the moles, again, of all the species that we're talking about to consider what's going to cancel out. Now for this problem, we can actually use the pH in order to figure out how much of the H3O we have in solution. And that's using the equation that the hydronium ion concentration equals 10 raised to the negative pH. And so that shouldn't surprise you that we're back at 1.8 times 10 to the negative 5, because that was the Ka that we used when we were trying to come up with this pH. So now we just need to remember that that molar concentration means moles per mil. So 1.8 times 10 to the minus 5 moles of H3O plus in 1 liter, and we know that we had 100 milliliters, or 0.1 liters, and we can use that to get the number of moles. Great, so we've done that for the H3O, but what about for the OH concentration, for those molecules that are going to be canceling out some of the H3O plus that we have? So when sodium hydroxide dissociates, we're going to get same number of moles of sodium as we get hydroxide, so we'll actually have 0.10 molar OH coming in that 1 mil, but there's only 1 mil of it, so we have to use our memory again that this is actually going to say 0.10 moles of NaOH or OH in 1 liter. And so we can multiply that by that very small volume, 0.001 liters, in order to get the number of moles of OH. And so that calculation is similar to the one that we did for part B, where we needed to get the number of moles of OH. And so now let's look at it. Let's look and see which of these numbers is bigger. We've got something times 10 to the negative 4 and something times 10 to the negative 6. Times 10 to the negative 6 is actually going to be a lower number, a smaller number, than the amount of OH. So we're going to have more OH than we have H3O at the end. So when we set these up, we're going to have the bigger number subtracting the little number and seeing what's left over. So if we do that with that larger amount of OH, only a little bit of the OH is going to be canceled by the available H3O+. So that means that we have that bigger number subtracting the smaller number of H3O. We still have OH left in solution at the end. We still have 9.8 times 10 to the minus 5 moles of OH. So now we can turn that back into a concentration. And so now we divided that number by the volume, the 0.10 liters. We now have a molar concentration of OH. If we want to turn that into something, we can't turn it into a pH. We can turn it into a POH. And so after we solve for a POH, we can convert that back into a pH. And so now at the end, we have a pH of 11.0, and so that is definitely going to be on the basic or alkaline side. And so I want you to compare that with what we saw with the buffered solution. In the buffered solution, we saw something go from a pH of 4.74 to 4.75. But with that same amount of sodium hydroxide added to an unbuffered solution, we switched from an acidic pH of around 4.74 all the way to a basic or alkaline pH of 11. So that's going to end this section of the lecture, and so now we can start to move on to additional examples of acids and bases coming together when we think about them in terms of titration. So you can go ahead and close this one and open up the next one.